Hey y'all, welcome back to another round of astronomy. Yeah, let's get going. Displayed for you, I have a news article regarding the Mars Climate Orbiter. And as you see, it's a accident that occurred in about the late 90s regarding a satellite that we wanted to put into orbit around Mars. Now, the interesting part, of course, is that you notice NASA made a unit error. And I should be more careful with that. It turns out that one of the contractors for NASA made a unit error, and it resulted in the loss of a $125 million orbiter. It's a bummer. And of course, you look here and it says, people sometimes make errors. That's a big error. And what happened, if you go through and read the congressional report, I believe, it was that one contractor was working in what is called the International System of Units, SI. In other words, meters, kilograms, seconds. Whereas another contractor doing a different part of the spacecraft was working in imperial units, feet, pound, and seconds. And so when the component working with the imperial system handed numbers off to the component that was using metric, it caused the orbiter to be lost. Be careful with your units. To walk you through, the first unit in astronomy that will be of some importance is what's referred to as the astronomical unit. As you see here, we abbreviate it with a capital A, capital U, and it is equivalent to a distance of 1.5 times 10 to the 11th meters. Now, I will assume that you're familiar with scientific notation. This 10 to the 11th, that's a 1 followed by 11 zeros. If you prefer kind of the everyday language, let's see, 3 zeros is 1,000, 6 zeros is 1,000,000, 9 zeros is 1,000,000,000. Okay? So this would be 1.5 times 100 billion. So this is 150 billion meters. It corresponds to roughly 93 million miles. Now you might say, Greg, where do we come up with that unit? Why do we come up with that? And much like the other units that we know and love, there's a physical basis historically for the unit. It's the average distance between the sun and the earth. The astronomical unit was chosen specifically for this reason. And it makes numbers when talking about the solar system very nice, not too large. For example, the distance from Jupiter to the sun is 4.5 astronomical units. In other words, 4.5 times the Earth-Sun distance. To Saturn, 10 astronomical units. Mars, 1.5. So it makes those numbers a lot easier to kind of manage and gives us a point of reference. Okay? So the next thing. So in part, we need to be careful about the units that we're going to use. And also you need to be a little bit familiar with how to convert between units. So I thought I would take those two and kind of mash them together for the next couple of questions. So a question for you. Okay? So the question, how many seconds are in a year? Okay? And don't memorize this, but rather I want you to be thinking about how do I set up this problem? So take a minute, pause the video, get an answer. You got it? Good, 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 good. So let's go ahead and now walk through the process. And there's an old joke. Okay? How do you eat an elephant? One steak at a time. Okay? Okay? So we are going to eat an elephant. Rather than going straight from a year to seconds, let's break it up into smaller steaks. And I usually think about 4 of them. Okay? I am not going to go from a year all the way to a second. I am going to go from a year to a day. I'll go from a day to an hour. I'll go from an hour to a minute, and I'll go from minutes to seconds. Okay? So break it up. Find the smaller steps, put them together, and that will allow you to get the bigger answer. Okay? So of course, I would be very impressed if you know right off the top of your head how many seconds are in a year. Okay? But I would be less impressed, no offense of course, if you know how many days are in a year, and then hours in a day, and et cetera, et cetera. So let's go ahead and fill these in. Okay? Now, we'll pause here for a moment. You might question, how do I know that I need to multiply, for example, 365 by 24? Okay? And here's the hint. You can treat units just like they're algebraic quantities. In other words, I need days to cancel. The only units I should have left over are years and seconds. Okay? I need that interceding unit, the one that I've kind of arbitrarily introduced in order to do the calculation. I need it to cancel out. And so what that means is that I put days in the numerator and I have to put days in the denominator for the next one. Okay? And that way I have numerator, denominator, I can cancel them out. And we can go through and follow this through. We have hours in the numerator and I have hours in the denominator. Minutes and minutes. So I'll go through and cancel those out, and I'll go through and do minutes as well. And at the end of the day, you see that we have 1 year, and then we have 60 seconds, seconds. So now we simply have to multiply up everything. We have the 365 times the 24 times the 60 times the 60. So I've just rewritten all of those. And you notice I still have seconds in the numerator and year in the denominator. Now we just do our fancy-pantsy calculators. Okay? And we see that we get something like 3.2 times 10 to the 7th seconds per year. If you understand the process, then it should not matter how familiar or lack of familiarity with the actual units being used. So let's take a look here. I say, hey, good practice. How many points are in a furlong? And I have shamelessly stolen this from Wikipedia. And you'll notice that a point is way up here in the top. I've indicated it with this white arrow. And then a furlong, which I believe it's a nautical term, I don't remember for sure, is down here, okay, at the bottom. And how you read this chart, this is telling you, for example, if you start at points, this chart tells you that there are 12 points in a pica. I start off with points, so I'll say 1 point, PT, is 12 picas. And I haven't done this before. I'm just running an example. And then you could say, okay, well, how many picas? I'll go over here to an inch. Okay? So I get that there are 6 picas in 1 inch. And we can keep going. Well, now we know that there's 12 inches to a foot, so we'll go ahead and do that. So times 12 inches to a foot. And notice again the pattern. I have a unit in the numerator. The next one I have it in the denominator so that the units will cancel out. Okay? And then, okay, well, we've got 3 feet to a yard. We don't have to look that one up. So now I'm right here. And, okay, let's go for miles. So, oh man, imperial system, such a bugger, right? I mean, this is silly. Oh man, imperial system, such a pain. Okay, 1 mile. And then we notice that there are 8 furlongs in a mile. So we'll say, okay, so that means that 1 mile is 8 furlongs. I'll just call it 8 furs. And now let's go ahead and double check. We'll go through. We see that picas cancel the picas. The inches cancel the inches. The yards cancel the yards. The miles cancel the miles. And so we'll have the number of points per furlong. Okay? So let's go through and do that. That's 12 divided by 6. And then we have another 12 in there. We'll just write this whole thing. We have a 3. We have a 1,760. And we have an 8. Okay. And again, I've goofed up the units myself, right? This is furlongs per points. Well, I want points per furlong. So instead of doing that, I'm going to flip it. In other words, invert it. Then that'll give me the right answer. I've got 6 times 12 times 3 times 1,760, all divided by 12 and 8. And that will give me the points per furlong. No, I haven't practiced this in advance. I have no idea what this is. Of course, the nice thing is, oh, goody, goody. Look at that. We get that the 12s cancel out, so we don't have to worry about that. Okay. And I'm sure that this 8, let's see. Yes, this 8 goes into 1760. So this 8, let's see here. What would this be? 220. So this 8 and this, I think this gives us 220. Right? 8 times 200 is 1,600 plus another 160. Good. So we see that at the end of the day, it's something like 1,320 points per furlong. Okay. Now go ahead. Okay. And if you feel a little bit queasy, a little bit of uncomfortable, go ahead. Pick another 2 on this chart. See if you can work your way between the 2. Okay. I don't know. How many poppy seeds are in a nail? Okay. Or maybe, let's see, maybe how many shackles are in a ramsden chain? I have absolutely no idea what these things are. Okay. So, but like I said, if you understand the process, the funky units won't matter. Okay. So practice it. If you have any questions, feel free to drop by the office. We can always work through a couple more as well. Okay? I will assume at this point you are comfortable with unit conversion. Incidentally, sometimes science classes will call this dimensional analysis. So if you've had a chemistry class, usually that's where you see a lot of it, dimensional analysis. Okay? Unit conversion. Cool. Well, we'll keep going here. Okay, so now we have how many seconds are in a year. Okay. Next question for you. There's a very special number that occurs in astronomy. I think that this is probably the most important number ever determined by physics, astronomy, etc., etc. Okay? Most important number, certainly in physics, 3 times 10 to the 8th meters per second. Okay. This is what we call the universal speed limit. It does not matter how hard you try. Okay. From what we understand, our current basis of physics and of the universe tells us that nothing can travel faster than this 3 times 10 to the 8th meters per second. Okay. It is known as the speed of light. So the question I have for you, I'm going to give you this. I'm going to say the speed of light, constant, and is 3 times 10 to the 8th meters per second. How far can light travel in 1 year? Go ahead, pause the video, take a minute. You got it? Good, good, good. And you say, okay, well, how do I work through this? You know this, okay? Distance equals rate times time. I'm pretty sure you've probably heard that before. If I want to calculate, for example, I'm going to grandma's house for Christmas. Okay, grandma lives, well, let's see, I'm driving for 60 miles an hour and I drive for 3 hours. How far away is grandma? You say, well, 60 miles an hour for 3 hours. Oh, I've gone 180 miles. Okay? Distance equals rate times time. Do the exact same thing for this problem. Okay? Except instead of driving at 60 miles an hour, you're going at a screaming, what is this? About 216,000 miles per second. That's 7 times around the world every second. So you're going a lot faster and you're traveling for a lot longer. Okay? But the whole idea, the process stays the same. So we get something that says distance equals the rate, the speed of light, times time, year, number of seconds in a year. Notice as well, the seconds in the denominator, again, cancel the seconds in the numerator. And before you pull out a calculator to actually do this, you should try to do it in your head. Okay? Notice, what's 3 times 3.2? Okay, forget about the 0.2. What's 3 times 3? 9. What's 3 times 2? 6. Okay? Now we put the 9 and the 6 together and move the decimal point over. You should get 9.6. This is also one of the benefits to doing scientific notation. You can ignore these powers of 10 for a moment and just focus on the numbers in front. Helps out with some of the mental multiplication. Second piece for scientific notation, if I take, this would be 100 million, 10 times 10, 1 followed by 8 zeros. Okay, that's 100 million. And I multiply it by 10 million, okay, I should get, well, 10 million, 100 millions. Okay. An easier way to say that is I add the exponent, the 8 plus the 7. Okay. So I get 9.6 times 10 to the 15th. This distance is given a very particular name as well. It is how far light travels in 1 year. So we call this a light year. Okay? So be careful. Okay? Be careful, be careful, be careful. A light year is not a unit of time. A light year is a unit of distance. Okay. Next piece. Okay. You could also do this if you want for a light minute. In other words, how far does light travel in 1 minute? You could also do what's called a light second. How far does light travel in 1 second? That one you already know. 3 times 10 to the 8th meters. A lot of the distances that we will be working with will be in light years. How far light travels in 1 year. Okay. To give you an idea about size, the sun is 8 light minutes away from the Earth. It's 8 light minutes, so it takes light 8 minutes to travel 8 light minutes. The sun could be snuffed out from the sky right now, and we wouldn't know what it looks like for another 8 minutes. We'd be sitting here, Star Killer Base could suck up the sun, and we'd be sitting here for 8 minutes until we realized something has happened. The flip side of that, the really cool thing, you ready? You don't see what the sun looks like right now. You see what the sun looks like 8 minutes ago. You, my friend, are a time traveler. Well, you get to see the past, maybe is a better way to say it. And that will be very important. You get to see the sun what it looked like 8 minutes ago. Okay. Further objects, we get to see further back in time. Polaris, for example, is about 400 light years away. So tonight, when you go outside and practice your star chart, you are not seeing the Polaris as it looks right now, currently. You get to see what Polaris looked like 400 years ago. Because the light that you see tonight has taken 400 years to actually arrive at your eyeball. Cool, right? Yeah, okay. So there will be another unit for distance in here. It turns out the light year, as large as it seems, is minuscule compared to the distances that we will be talking about in this class. We'll start with the light year, but at some point we're going to have to transition to a larger unit. And the reason for it, again, is to make the numbers look a little bit nicer. Okay. To be continued. Now, in addition to distances, astronomical units, and light years, we also need finer angular measurements. Recall that from the star chart lecture, we talked about using your fist at arm's length. This is about 10 degrees. But astronomers need finer divisions of an angle. Okay? 1 degree is too large for precise astronomical measurements. So astronomers use what is also called an arc minute. It is 1/60th of a degree. You can imagine taking your pinky, slicing it up into 60 segments, taking one segment out. That would be an arc minute. Of course, that is not precise enough for astronomers either. So we can take 1 arc minute and slice it into 60 pieces, and astronomers call that an arc second. Okay? So it's 60th of a 60th, or 3,600ths. Incidentally, these are also used for latitude and longitude. If you go and look at a GPS coordinate for any object, you will get the angle in degrees. Then there tends to be a dot, and then you'll get the arc minutes. Notice that the hash mark is used for arc minutes, not feet. And then you get a double hash for arc seconds. Okay. Pretty cool, huh? Good. Now I have this last distance measurement to give you, and I needed you to know what an arc second is in order for this to make sense about what the physical basis is. So here it is. This is called a parsec. Okay? 1 parsec, abbreviated PC, is 3.2 light years. I'll give you the physical basis. Okay? The physical basis. How far away from the Earth do I need to be such that the sun and the Earth are the separation between them is 1 arc second. So imagine jumping into your spacecraft. You fly well out beyond the boundary of the solar system. You turn around, you point at the Earth, you point at the sun, and the angle between your 2 arms is 1 arc second. That, when that happens, you are a distance away from the Earth of 1 parsec. To give you an idea about the vastness of space, you're not even to the next closest star. Okay? The next closest star is about 4 light years away, or about 1.3 parsecs. Okay? Last thing that I'll give you here is what's called a solar mass. Okay? Again, kilograms, too puny of a unit for us. When we talk about stars in this class, it will generally be in terms of in comparison to how large our sun is. So what we have is a solar mass, and it's about 2 times 10 to the 30th kilograms. Okay, so that pretty much takes care of the units piece. Okay, the various units that we're going to see pop up. But the other thing I should probably mention is the prefixes that we sometimes put in front of units. Okay. Now we'll see these pop up as we go through, and I just figured I would give you the chart. You should probably be familiar with some of these already anyway, but I just, for completeness, give you the chart here. So each of these, I've given you the prefix in parentheses. And again, that's because scientists are lazy. We get tired of writing times 10 to the blah. Okay, so we do these prefixes instead. So the equivalent, the numeric equivalent, the powers of 10 are given here. I always get upset, right? Like I'm walking through the gas station and they tell me that there's a mega millionaire jackpot. And I think, well, gee, they're lying to you, right? Because like the jackpot's only 100 million. But mega millionaires, like mega millionaires, that's 10 to the 6th times 10 to the 6th times 10 to the 6th times 10 to the 6th. That should be like, you know, more money than exists in the entire world. I feel lied to. No? Okay. I will warn you, a couple of these, you can go really large, which will happen when we're talking about distances in the universe. We'll also go really small, nano and micro, because we're going to have to discuss properties of light. And so when we're doing that, we're going to be using nanometers or maybe micrometers. But when we're talking about sizes of the universe, we're going to run into units like megaparsecs, gigaparsecs, so 1 billion parsecs. Okay. So stay tuned, but figure I'll give you that. Okay, so some questions for you. Now don't look at your notes. You need to come up with this on your own. Recall, okay? Low stakes, but you got to recall it. You just heard about it. What's the physical basis for an astronomical unit? You got it? Yeah, so we'll start there. Don't forget, an astronomical unit is the Earth-Sun distance. Okay? The distance between the Earth and the Sun. Next question for you. Okay? Here's the GPS coordinates for Denver, Colorado. Okay? So you notice again, degrees, and then we have some extra numbers following. Okay? Round it to the nearest degree. You got it? Yeah, good. Pause it if you don't, of course. Okay? But let's remember that we have right here, these are arc minutes. Okay? And how many arc minutes are in a degree? Yeah, 60. Right? Remember, there are 60 arc minutes in 1 degree. Okay? Or you could say that 1 arc minute is a degree divided by 60. Okay? So the question, should I round 45 arc minutes? Should I go up to the next degree or should I go down? Yeah, good. Yeah, you should go up to another degree. So right here, we should round that to 40 degrees. So we'll say that it's at 40 degrees. Well, how about, yeah, you got it? Same thing, good. So we should say that Denver, Colorado, it's roughly 40 degrees north and 105 degrees west. Don't worry if you got that wrong. The whole reason I asked this question is because the most common answer is probably 39 degrees and 105 degrees. Okay, right? You say this is less than 50, I'll round down. Oh, nay. Don't forget, it's 60 arc minutes in a degree, not 100. Okay? Keep going along with that. And in lab, for example, I'll say just round to the nearest degree. That's fine. Okay? But just wanted to highlight that for you so you can start kind of getting a feel for it. Okay, well, that's all I have to say about units for the time being. I thank you for your attention. Keep up the good work. I'll see you next time.